This video focuses on using carbon-13 chemical shifts for stereochemical assignments. As we've seen in a couple of the earlier videos, for proton NMR spectra, axial hydrogens are shielded relative to equatorial protons. The same effect is observed with carbon-13 chemical shifts. For 1,4-dimethyl cyclohexane, for the cis isomer, at room temperature and slightly above room temperature, the rapid ring flip between conformations gives a sense of symmetry so that the methyl groups are homotopic and share the same chemical shift. But at lower temperature, the rate of conformational interconversion is now sufficiently slow so that each methyl group is distinguishable in the NMR spectrum, with the axial methyl group shielded relative to the equatorial methyl group. In the previous module, we worked through identifying proton chemical shifts for axial versus equatorial methyl groups. And we can also do this for the carbon chemical shifts. I've shown the carbon NMR spectra for the trans diastereomer of tetrahydrocannabinol, and at first glance, the carbon spectrum for the cis diastereomer is probably indistinguishable. Going back to the spectrum of the trans THC diastereomer, we see that there are 8 carbons that are downfield of the chloroform peak. It turns out that there is 1 carbon that overlaps the chloroform peak. And then there are 12 more carbons that are upfield of the chloroform peak, for 21 carbons altogether. If we compare with the cis THC, once again we have 8 carbons which are downfield of the chloroform peak. We can now see that there's a peak for the cis that is just to the right of the deuteriochloroform peak. And then we see what appears to be 11 peaks that are downfield. Although since we know these are stereoisomers, it turns out that one of these peaks, and I believe it is this one, is actually 2 carbons. So we can use the letters J through U once again. It may be easier to see differences if we overlay the 2 spectra. So here we have cis THC on the top and trans THC on the bottom. And while you can see that these are still similar, there are now some differences. Not just the appearance of this peak at 77 parts per million, that stands out in the cis THC, but there's a big difference in that one of the peaks for trans THC is deshielded down at 46 parts per million, and that's not present in the cis THC. Let's look at the spectrum in portions. All of the carbons to the left of 100 parts per million are sp2 hybridized, and thus are quite substantially deshielded. Based on the structures of cis and trans THC, there are 6 aromatic carbons and 2 alkene carbons. We can actually make some estimates for the aromatic carbons by applying the substituent rules for aromatic compounds from table 4.12. Now, the substituent effects are not going to account for stereochemistry, but we'll compare with the values for trans THC since that has been better characterized. We also have to make some approximations. At carbon 1, the substituent resembles an isopropyl group. And so we'll apply the correction factors for the isopropyl group for carbons 1' through 6'. At carbon 2, there is a phenol, so we apply the correction factor for the hydroxyl group at 2'. 3' has a hydrogen, but 4' has an N-pentyl group. And the closest thing that fits in table 4.12 is the ethyl group, and I just use CH2 as the abbreviation, and at 4' it has the biggest effect. 5' is substituted with a hydrogen, and then at 6' we're substituting with an ether alkoxide, and that accounts for this correction factor. If we now look at the specific peaks as labeled, for 2' calculated and observed are very close, not quite as close for 6', but we can say with a fair degree of confidence that A and B are 2', 6', without necessarily assigning them specifically. The peak at 143 correlates quite well with being C. And then we have 3 peaks that are observed around 110. 1' doesn't fit as well as 3' and 5', but FGH look like they could fit these 3 peaks, and in particular G, without an NOE, corresponds with what we would expect for the 1' peak, so that F and H are 3', 5' without necessarily assigning them. We still need to assign D and E. However, D would fit for carbon 3 since it's a weaker signal without NOE, whereas E fits for carbon 2, which is bonded to a hydrogen. Thus, with HMQC alone, we already have good candidates for 8 of the carbons and unambiguous assignments for 4 out of those 8 carbons. The next peak that we can assign is this peak that is just to the right of deuteriochloroform in cis THC, and that fits for a quaternary carbon which is attached to an oxygen. If we had access to the original data for trans THC, we could probably find the corresponding peak hiding under the deuteriochloroform peak for the corresponding carbon 7. So that is a 9th carbon that is now assigned. The next section of the spectrum that we can analyze is from 50 to 30 parts per million. In trans THC, we see 6 carbons. If we do the easiest thing to make some estimates for the N-pentyl group, well, starting with pentane and putting on a phenyl substituent at the 1 double prime position, we see that there's fairly good agreement between calculated and observed for 1 double prime, 2 double prime, and 3 double prime. Note that 2 double prime, which is closer to the phenyl group, is actually shielded relative to 3 double prime. From this analysis, we can say that carbon J is probably not on the N-pentyl group. And is consistent with the assignments that were made for M, O, and K, respectively. The position where we see the biggest changes are for carbon J at 46 parts per million in trans THC and at 40 parts per million in cis THC. These are both unique resonances, so it is possible that it is carbon 6, which is the position where these two compounds have different relative stereochemistry. It still remains to make a tentative assignment for carbons L and N, but we have two allylic carbons which are deshielded by proximity to the alkene, and with additional information from a depth spectrum, which is not shown here, we can assign that L is carbon 1 with the single proton attached to it, whereas carbon N is carbon 4 with 2 hydrogens attached to it. We can now analyze the carbons that are most shielded in the spectra. There are 6 of these carbons apparent in both diastereomers, and by focusing on just 6 resonances, we can see similarities and differences. We've already estimated that the terminal methyl group of the N-pentyl group will be quite highly shielded, around 14 to 15 parts per million, and so we'll assign that as U in both diastereomers. And then the 4 double prime of the pentyl group was estimated to be about 23 parts per million, and that fits for S, which is present in both diastereomers. The depth spectra are not shown, but those reveal that P, R, and T are carbons with 3 hydrogens attached to them. So those are methyl groups. If we compare cis and trans diastereomers, P and T are actually the most different of these. We see a larger difference in relative chemical shifts for P and T for the trans THC, suggesting that P is equatorial and T is axial. But the difference is not as great in the cis diastereomer, where we've already seen that there is not as big of a difference between axial and equatorial methyl protons. If you can imagine a 3-dimensional structure for the trans diastereomer of THC, carbon 8, which is trans to the adjacent chiral center with hydrogen, fits for an axial methyl group, and C9 then fits for the equatorial methyl group. The remaining methyl group is consistent with the allylic methyl, which is attached to carbon 3. And then we simply have left carbon Q, which may fit for the carbon labeled 5. And a depth spectrum could tell us that Q is a methylene or a CH2. While I've attempted to make claims for all of the carbons, some claims are stronger than others. Some of the claims are relatively weak and should be considered hypotheses. But at least we have a starting place now when we get additional information from other two-dimensional NMR experiments. I'll finish this video by describing how we can use carbon-13 chemical shifts to assign the relative stereochemistry of acetonide derivatives arising from diols. For 1,3-diols, which form acetonides, we can make assignments based on whether the oxygens of the diol are 1,3-cis or pointing in the same direction, or 1,3-trans or pointing in the opposite direction. If the hydroxyl groups are pointing in the same direction, then the acetonide will be chair-like with clear equatorial and axial methyl groups. On the other hand, if the hydroxyl groups are trans, then the conformation of the acetonide is likely to be a twist instead of a chair. And the methyl groups will be more similar, neither being clearly axial or equatorial. There is an additional subtle matter with carbon-13 chemical shifts, but it does hold up over a fairly large number of compounds. The more strained the acetonide is, the more deshielded is the central carbon. And so for the twist conformation, the chemical shift tends to be slightly greater than 100 parts per million, whereas for the less strained chair conformation, the chemical shift tends to be just under 100 parts per million. The ring strain correlation can also help us distinguish between 6-membered ring acetonides around 100 parts per million and the more strained 5-membered ring acetonides, where the chemical shift tends to be closer to 110 parts per million. I've also made some tentative assignments to the carbon spectrum of this compound. For the alkenes A and B, A gives a weaker signal consistent with less nuclear spin over Hauser effect with only one hydrogen attached to carbon A versus B with 2 hydrogens attached to carbon B. This could be confirmed if we had access to a depth spectrum. In addition to assigning carbon C, carbons D and E around 77 parts per million are consistent with the methine carbons bonded to oxygens. But we can't really distinguish which one is D or E without more information. However, F fits for a primary alcohol carbon. G may be the allylic methylene group. Again, it would be nice if we had a depth spectrum to show that it is a methylene and not a methyl group. But then I is assigned as a pseudo-axial or shielded of the methyl groups, and then H is a pseudo-equatorial, less shielded of the methyl groups.